a presentation on solar weather propagation. First of all, my name is Steve Horish. I'm KE0VDC. I'm from Rosemont, Minnesota. I'm a member of the Twin Cities Repeater Club in Burnsville, and all of my comments are in the speaker's notes, which will be part of the presentation file distributed after the conference. A quick disclaimer, I am not formally or informally trained in any of this. I'm just a ham who got interested and started investigating, and I'm just sharing what I've discovered. HF propagation is affected by what we call weather on our sun, and the question has always been, why is this so? And what are the mechanisms involved? And can we use the numbers we see of solar weather conditions that are posted various places to help us understand when HF propagation is going to be particularly good or maybe not as good? And important place to start, obviously, is at the sun itself. And so our sun is a main sequence G2 class star, sometimes described as a yellow dwarf. Compared to other stars in our galaxy, it is entirely unremarkable. It's about 4.5 billion years old and will remain in its main sequence for about another 4 billion years. And stars within the main sequence fuse hydrogen into helium, releasing energy in the process. So the sun fuses about 600 million tons of hydrogen per second and produces about 596 million tons of helium in the process. The net loss is about 4.25 metric tons of matter per second, and that is converted to energy. And if you actually use the famous E equals mc squared equation, it works, and it will tell you that it produces about 384.6 yada watts per second, 385 times 10 to the 24th watts. If you try to put that in perhaps a more convenient unit of measure, it's about equivalent to about 90 billion megatons of TNT per second. So there's a lot of energy being released. The fusion process takes place deep within the core of the sun, and because of the extreme density gravity and intense magnetic fields, the energy released takes as long as 100,000 years to reach the surface and radiate into space. So what we see is energy that was released many thousands of years ago. Now, this process creates an extremely strong magnetic field, and it does a great job generally of containing this extremely energetic process. Normally, we just see the sun as this smooth orange ball and with light coming out of it. However, for reasons not yet fully understood, the magnetic field of the sun reverses itself on an approximately 22-year cycle, flipping polarity about every 11 years. And then 11 years later, it flips back to where it was. 11 years is an average. The measured range has been as short as 8 years and as long as 14 years. So it's not like you would set your calendar by it. Solar cycles are numbered, beginning with the first critically observed and documented cycle in 1755. We are currently approaching the maximum of cycle number 25, which should peak sometime in the year 2025. As this process initiates, the magnetic field becomes increasingly disorganized, and some of the normally internal processes kind of leak to the surface and become visible. And we observe this in several ways. First of all, the appearance of sunspots. There are areas of extreme magnetic field density. The magnetic field there is so dense, in fact, that it chokes off that surfacing of energy from below. It just doesn't allow the energy to rise to the surface. And as a result, the areas are slightly cooler than the surrounding surface, but they're typically the launching points for all of these other solar misbehaviors like solar flares and coronal mass ejections and arcs and all kinds of high intensity events. Another anomaly is that the radiative output of the sun in the UV and X-ray parts of the spectrum increases markedly, as much as 10x. So that part of it goes way up. And so the first thing we'll talk about is this number you'll see, which is called SN or SSN, and it's the sunspot number. One would presume that it means this is the number of spots on the sun, but it's not that simple. It's actually a formula, and it consists of a sum of two scores. You score 10 points for each group of sunspots, and then one point for each discrete sunspot within those groups. So a single sunspot on the sun is one group of one, or a SN number of 11. The rule of thumb is when you see the SN number, divide it by 15, and that'll get you pretty close to the actual number of discrete visible sunspots. We will see solar flares. Solar flares are ruptured magnetic lines. They expel vast amounts of energy in matter. They're a directed phenomenon, and most of the time they miss us. They aim someplace else, and we're not affected by it. But once in a while, they do impact us. Geomagnetic and electromagnetic aspects may impact us, even on a near miss, because they are fairly, shotgun kind of effect. And oftentimes these things will result in things like radio blackouts. The output is in three spaces. It's in the geomagnetic, it is electromagnetic, and it is a sharp burst of UV, and it's also particulate in what we consider to be the solar wind, which is actually particles ejected from the sun at high speed. Another phenomenon we'll see are these things called coronal mass ejections, and that's a situation when physical material is ejected from the corona of the sun, usually by an intense magnetic field. The lines will burst and it will cast out material headed towards Earth or wherever. If they're Earth directed, they can cause radio blackouts. So the solar wind travels at speeds from typically around 200 kilometers per second to as much as 3,000 kilometers per second. So these things are really moving. A typical coronal mass ejection, in terms of how much mass is there, it's about 1 billion tons in a typical CME. And at solar maximum, there are on average about 3.5 CMEs per day. So there's a lot of stuff going on. We will talk about coronal loops. Coronal loops, they're just arcs that are basically current flowing through a loop. And it's a loop of plasma and in a very, very intense magnetic field. And the current flowing through one of those loops, the best numbers I can find are somewhere between 10 to the 17th and 10 to the 19th amperes. So pretty intense stuff. They originate near the sunspots, and they can sometimes snap and initiate a solar flare. And when that happens, that loop essentially closes in the broken off part, and it memorizes the magnetic polarity of whatever that loop was. And then when those coronal arcs like that impact Earth as a solar storm, what we will see and how it will affect Earth will depend upon whether the contained magnetic field aids or opposes that of the Earth. If it opposes that of the Earth, sometimes they'll largely cancel each other. Otherwise, it has a particularly strong effect if it aids our magnetic field. We'll talk about solar output. The output of the sun falls into three general classes. First of all, there's electromagnetic. That is radiation that spans primarily from infrared into the ultraviolet and soft X-rays. There are also some minor spikes of emission in the RF spectrum. As the sun approaches solar maximum, this output increases, particularly in ultraviolet and X-ray part of the spectrum. Since these are the energies that form and maintain our ionosphere, these increases directly derive changes in the ionosphere itself. Some of these changes improve radio propagation, while others detract from it. It depends on exactly what's going on. We also have output in the geomagnetic space, and the immense magnetic field of the sun is very dynamic during solar maximum. And these waves of magnetic energy reach the Earth and affect both the ionosphere as well as the Earth's magnetosphere. Our ionosphere is a diffuse plasma, which is somewhat conductive. So magnetic lines, particularly variable magnetic lines, cutting across our ionosphere, induce currents and actually move our ionosphere a little bit. The third domain where we see output from the sun is in the particulate domain. And that is actual matter ejected from the sun, and it can be solar wind, it can be coronal mass ejections, Solar flares will throw matter out into the Earth, out into the in space as well. These high energy particles affect both the ionosphere as well as our magnetic field. And the physical pressure of both the solar wind and the CMEs further distort and compress the ionosphere as well as our magnetic field. And all of these classes peak during solar maximum, collectively having effects on the Earth. And at this point, it would be appropriate to observe that we actually live in rather a rough neighborhood. There's a lot of the sun is rather an unruly neighborhood, and there's a lot of big stuff going on there. We have to talk about the Earth. Our Earth is a rocky planet orbiting the sun about 93 million miles distant. It has both a significant atmosphere as well as a formidable magnetic field, and these two traits together combine to protect the surface of the planet from the most deadly effects of the sun. And our atmosphere blocks a large percentage of the ultraviolet radiation reaching the Earth, and releasing the energy of this action ionizes the upper atmosphere into a layer we refer to as our ionosphere. Let's see here. We have a magnetic field around it. We call it the magnetosphere. It is the Earth's magnetic field. And back when we were in about third grade, they told us, hey, it's just like this bar magnet, and it's got these nice round lines, and that's what our magnetic field looks like. And if the Earth were existing all by itself out in void of space, that's probably what it would look like. But we have a tremendous interaction between our magnetic domain and that of the sun. So the magnetosphere of the sun impacts the shape of ours. So basically, when it interacts with the sun's intense magnetic field, it's greatly distorted, and the magnetic environment bows into is warped into something that creates what they call kind of a bow wave. It basically creates a front against the sun. And that magnetic energy facing the sun diverts much of the solar wind from the sun around our planet. And the solar wind is a constant stream of charged particles, mostly hydrogen ions, arriving from the sun between 200 and 400 kilometers per second. That's between 450,000 and 900,000 miles per hour. Left unchecked, the solar wind would soon strip the Earth of its atmosphere, leaving it uninhabitable. Geologists tell us that Mars once had an abundant atmosphere, but the lack of a Martian magnetic field left it unprotected from the solar wind, which eventually depleted it. The other particulate output of the sun is in the form of coronal mass ejections. Those are violent expulsions in the solar atmosphere, and typically contain between 1 billion and as much as 100 billion tons of charged particles. These ejections are typically much faster than the relatively placid solar wind and can reach speeds of as much as 3,000 kilometers per second, or about 6.5 million miles per hour. Collisions of CMEs with the Earth can easily overwhelm our magnetic field, allowing the matter to spill into the upper atmosphere at very high speeds. And one of the typical side effects of this is spectacular aurora displays when all of that stuff hits our atmosphere. We talked about the ionosphere, and it's basically described as being a series of layers of sparse plasma at the very top of our atmosphere. The ionization is basically driven primarily by UV and soft X-ray components of sunlight. The layers have a secondary effect of selectively refracting or absorbing radio waves of specific frequencies. And under the right conditions, this allows long-range communications throughout much of the HF spectrum in the amateur bands. In similar ways to the magnetosphere, the ionosphere is also impacted by both the magnetic fields of the sun as well as solar winds, causing it to sort of smear from a perfect circular shape into something resembling sort of a teardrop. We typically describe the ionosphere as containing designated layers, and each of these layers has a specific effect on radio propagation. And if we start from the inside, nearest to Earth, the first one we'll encounter is the D layer. And the D layer ranges from about 30 miles to about 56 miles above the surface of the Earth. It consists mostly of ionized nitrogen and some oxygen. These ions have a relatively short lifetime, meaning they rather quickly recombine and become non-ionized. And the net result of that is that the D layer disappears at or near sunset. When the sun stops impacting that layer, it just basically dissolves and goes away. And that the D layer actually attenuates medium frequency and on the lower part of the HF, mostly below about 10 megahertz. And it's responsible for HF bands being what they call short during daylight hours, as it effectively blocks distant skywave propagation of both signals and noise. And then as daylight wanes, these bands are typically described as quote unquote going along. And what happens is the D layer dissipates and we suddenly can reach out to the ionosphere, the upper layers of the ionosphere, and we suddenly hear the world. The next layer out is the E layer. Consists mainly of ionized oxygen resulting from soft X-ray solar emissions. It's from about 56 miles altitude to about 93 miles altitude. It's reflective at lower frequencies, but since these are heavily suppressed by the D layer below it, the overall effect during the daylight hours is minimal. We don't even know the E layer is there because we can't reach it. The ions within this layer have lifetimes in the range of a few hours. As night falls and the D layer dissipates, the E layer rises in altitude and it affords skywave propagation at medium frequency signals. If you look at any older texts, you may see something referred to as the Canaley heaviside layer. That is the E layer. A more relatively known portion of the E layer is what's called the E sub S, or the sporadic E layer. This consists of very highly ionized clouds within the E layer, which can often reflect radio waves up to 50 megahertz and occasionally as high as 450 megahertz. The exact mechanisms that form these sporadic E clouds is largely unknown and subject to considerable debate. Clouds have a lifetime from as little as a few minutes to several hours, and they may span as little as a mile or up to hundreds of miles. And they typically form around the summer solstice and to a lesser degree around the winter solstice, so midsummer, midwinter. For reasons unknown, they are somewhat more prevalent in years near solar minimum. So we don't see as many of them near solar maximum, and that's another bit of a mystery. At the top of the ionosphere is the F layer, which extends from about 93 miles to about 310 above the Earth. And this layer has the highest electron density of all the layers. It's formed by extreme UV radiation from the sun. Carriers within this layer are primarily ionized oxygen, and they have lifespans of many hours, thus persisting pretty much through the night, even after the sun sets. This layer splits into two layers during the day, an F1 and an F2 layer, and recombines into a single F layer at night. It is highly reflective HF radio signals below specific frequencies. And a couple of little trivia points here. First of all, you hear people refer to the ozone layer. That's basically inside the D layer. That's from about 9 to 18 miles up, so it's well inside the D layer. And another point of interest is that the International Space Station orbits at around 250 miles. So that's just inside the F layer, the very top of the F layer. So that kind of gives you a sense of scale as to where all these things fit. We talked about radio waves being refracted below a certain frequency. We call that frequency the maximum usable frequency, or MUF. And frequencies up to the MUF will be refracted back earthward, while those above the MUF are most likely to penetrate the ionosphere and exit into space. And MUF is a localized measurement, not global. And as a result, it's useful to have a source of relatively local measurement. I've got the one I use here is from kc2g.com. And it basically, you'll see all of the different measurement stations. The closest one to us is in Alpena, Michigan, which you see just to the east of the Great Lakes up there. So that's probably the best reference for us in terms of that's probably what our MUF is locally here. Another bit of an aside, on that same page, there is a tab called FOF2, and that describes something called the critical frequency. That just happens to be the upper cutoff frequency of NVIS propagation. So if you have an antenna that uses near vertical incident skywave as its mode of propagation, that will tell you the maximum frequency at that particular time for which you can use NVIS as a mode of reflection. Another number we talk about is solar flux index, and it's a measure of the sun's relative output of UV and X-ray. The ionosphere itself reacts to the varying UV and X-ray output of the sun by varying its thickness, basically. We measure the output of this from the sun as something we call solar flux index, or SFI. Direct radiometric measurement of this is very difficult because both the UV and X-rays are heavily attenuated by the ionosphere, so we don't get to measure them down here. And to complicate matters further, higher radiation values thicker the ionosphere and increase the degree of attenuation, so it's nonlinear. So solar observers rely on a novel trick in this case. As UV and X-ray radiation levels increase, so do emitted RF levels in the microwave part of the spectrum, particularly around the 10.7 centimeter or 2800 megahertz range. So by measuring the emissions at 2800 megahertz and scaling up appropriately, we get a very accurate estimation of the actual UV and X-ray output. And the derived radiation levels are expressed in solar flux units. They range from as low as maybe around 50 during solar minimum to values around as high as 300 during solar maximum. You'll see the measurement expressed as SFI on space weather sites. And as a general rule, the higher the SFI, the thicker the ionosphere layers, and the higher the MUF and the more reflection that goes on. SFI is a linear unit of measurement. You'll also see these things called K and A, and they're complicated by the fact that they're multiple measurements. As the magnetic field of the sun becomes disorganized during solar maximum, it's easy to assume that it means the magnetic field of the sun somehow goes away, but it really doesn't. It just generates into a wide array of local maxima and minima, and making the magnetic field of the sun look more like a hedgehog. It's just little spikes sticking out all directions. And as the sun rotates on its axis, which is about every 27 days, the Earth is swept by all these peaks and valleys. And add this to the snap, crackle, pop sound of coronal arcs and solar flares, and all of these other magnetic outbursts from the sun. And the result is a very noisy magnetic signal that impacts both the Earth's magnetic field as well as our ionosphere. What happens is the magnetic chaos in the sun effectively ends up modulating its radiated magnetic field. And because of the strong coupling between the sun's magnetic field and ours, the modulation is transferred to our magnetic field and ionosphere. Now, this manifests as basically radio noise and as a disturbed ionosphere. We tend to think of the Earth's atmosphere as this placid ocean of air above us. In fact, it can be rather violently disturbed, much as our oceans are when a storm passes. So the magnitude of this solar magnetic disturbance is expressed in lowercase k index, and it's measured by 13 observatories around the world. So at any given time, there are 13 K values. The measurement is logarithmic in nature, so that a reading of K2 is 10 times more magnetic field disturbance than, say, a K1 reading. Note that the K index is measuring the resultant disturbance of the Earth's magnetic field due to the solar magnetic activity. So it's measuring our magnetosphere, not the sun's. And but knowing this at any one point is somewhat less value than knowing it globally. So there is this second value called K sub P, which is the planetary K. And it's just the average of all of the individual measurements across all the observation sites. The case of P scale ranges from 0 to 9, with 0 being very quiet and 9 being a very, very major solar storm. Also related to this is something called the A index, which is a linearized K index measurement. The A sub P index is averaged over a rolling 24-hour period. And in much the same way as the oceans of the Earth remain disturbed after the passage of a storm, the same thing is true of our ionosphere. Once it gets churned up, it takes it a while to settle out. So the A index takes this into account and reflects a settled value of the residual magnetic disturbance. Like the K index, it's both local, and there are both local and average global measurements. In this case, the global measurement is A sub P, or planetary A index. K sub P and A sub P values can be correlated, and that the chart that's shown there shows you how they line up. The K index is an indirect measurement of geomagnetic storms on the sun. We're measuring the effect on the Earth's magnetic field. Actual measurement of the strength of the magnetic storms on the sun itself is measured on the G scale, and it's a direct correlation between the K index and the G rating of the associated magnetic storm. It's just one is just slightly weaker than the other. K sub P values or planetary K values of 5, for instance, correlates to a G1 level storm on the sun, while a planetary K of 9 indicates a G5 level magnetic storm, which would be very severe in terms of its consequence to radio. The other area, those are the electromagnetic and geomagnetic fields that disturb our ionosphere. The third dimension is the particulate, and this is the output of the sun. That is, we think of as the solar wind, or it's measured on the S scale, which stands for solar proton flux. And it's basically a measure of the number of charged protons arriving at the Earth per second per unit of area. And solar radiation storms can be a result of solar flares, which span all 3 output classes, as a matter of fact, as well as just solar radiation storms and coronal mass ejections. The S level is a logarithmic scale and consists of values between S1 and S5. And so again, it's, an S, because it's logarithmic, an S2 is 10 times more impactful than an S1. And it's a measure of the high energy particles impacting the Earth, and all of these are measured as a variation from a baseline solar wind level. So S1 is basically just the baseline solar wind, and then we can get increasing levels above that. All of these things, the K, the A, the G, the S, these are all detractors from propagation because they disturb the ionosphere and cause it to thin out, and or to be so disturbed that that the refractions are diffused. So now, what does all this mean? What do we do with all this information? Well, one of the things that I did here was I listed them all as what domain they're in. They're geomagnetic, they're electromagnetic, or they're particulate. What the parameter is we're measuring, and I gave you an ideal value of what a perfect day of dx would be, and then I gave you what I would call a good range. And so reasonable propagation requires good activation of the ionosphere, so a fairly high solar flux index, without geomagnetic or particulate disturbances. However, the primary driver of high solar flux index, which is SN, or sunspot number, also tends to drive higher levels of the under indices as well. So we get the good along with the bad. An SFI as low as 100 can begin to open 10-meter band, but reliable ongoing openings usually require a number closer to 150. At 100, you'll get single hop skip out to maybe Europe or South America, and when you get out to 150, then you're going to get the multiple hop well into Asia Pacific and Central Asia. It's going to take 2 hops to get there. So those are kind of the numbers that you wish you would see. Now, where do you get these numbers from? So first of all, on QRZ, there's this applet put there by N0NBH, or N0NBH, and it has a lot of data crammed in a tiny little space. And I've labeled where all of them are, where the solar flux index is, where the sunspot number is, and AP, KP, G index, and MUF are all kind of crammed in that little space. And that's a good place to look for just a quick view of how the solar weather is doing at the particular moment. This updates fairly frequently. There's also the National Oceanographic and Atmospheric Association, or Administration, I'm sorry. NOAA puts out basically a series of dashboards, and they have a website here that is basically space weather. And there's a series of dashboards, among other things. This particular one is called the Space Weather Enthusiast Dashboard. And I like it in particular because it has the three output classes: the electromagnetic, the particulate, and the geomagnetic, right there side by side, along with basically a 3-day forecast of what they think the K index might be and what they think the S index might be, and those sorts of things. So that's a convenient place to look. Their forecasts of the K index are usually pretty good, and it's easier to look forward and know ahead of time when the good propagation things are going to occur, rather than discover that 3 days ago you should have been listening. Another thing that's on the bottom of that very same one are a couple of graphs that show basically how cycle 25 is performing, both in terms of sunspot number and in terms of solar flux index. And as you can see, cycle 25 right now is outperforming its original predictions. We're getting much better stuff than we thought we would. And so right now, nobody knows what that means. There's three possibilities. One of is that it might be a short cycle. It might be one of the 9-year instead of 11-year cycles. It could also be that it is more like 2 cycles ago when we had two peaks, basically a peak and a lull and then a second peak. It could also mean that it's a real barn burner like cycle 19 was, where everything goes off the map and we have an absolutely fantastic solar cycle. We just don't know right now. Time will tell, and we'll just have to put up with what we get. There's also a radio communications dashboard on that same website. And that one is one of the things I like about it is you get a direct measurement of the D layer here. It'll tell you how intense the D layer and what the cutoff frequencies are at any particular time, day or night, and where the D layer is in effect and where it has dissipated. So that's kind of handy to have particularly if you're interested in NVIS kinds of propagation. There's also a tab called Products and Data, and that has a lot of great stuff in it, including some long-term predictions, like some 27 to 30-day predictions and forecasts on what they think certain parameters are going to be. And those are a bit speculative, but they're still a good source of information.